This is chapter 4 on the video pamphlet called Agonist Efficiency. And in the first chapter, we defined it as the ratio of the weak to strong binding energies. In the second chapter, we described some patterns of agonist efficiency, that there are classes and multiple classes in muscle-type nicotinic acetylcholine receptors. In the third chapter, we traced its origins to a linear free energy linkage between catch and hold, which are respectively parts of the binding and gating reactions. And in here, we're going to extend what we've learned about the origins of efficiency into the rest of the gating isomerization. So this chapter is entitled Implications of Agonist Efficiency. So the subtitle of the pamphlet is Reflections on the Motive Power of Agonists, which is a takeoff on the 1824 pamphlet by Sadi Carnot called Reflections on the Motive Power of Fire. Carnot was trying to understand how a difference in heat could drive a piston. So William Thomson, or Lord Kelvin, really liked that pamphlet, and he named the field of these reflections, called it thermodynamics. So we're going to be talking about reflections on the motive power of agonists, and so perhaps that field of how agonists turn on receptors could be called chemodynamics. The first two chapters really focused on the chemo part of chemodynamics, that is, what were the energy changes experienced by the agonist during the activation process. And in this chapter, we're going to switch over to the dynamics part, which is how does the protein actually change its conformation from closed to open, and that's going to be the focus here. So if you're interested only in the agonists, then you really don't have to listen to this chapter. This chapter is going to have very little to do with the agonist and much more to do with the protein itself. So this is where we left off in chapter 3. Both binding and gating had been subdivided into intermediate states and processes. Here in this reaction scheme, the asterisks reflect intermediate states, and the rectangles represent intermediate processes that separate these intermediate states. So binding had been divided into diffusion, which was the same for all the agonists that we were considering, and a second conformational change called catch, which establishes the low affinity complex. And gating had been separated into hold, which is the switch of the binding site from low to high affinity, and a number of other processes which we will enumerate in this chapter. We will give each of these, the blue, green, red, and brown rectangles, we'll give them a name in the course of this chapter. And catch and hold were linked by a linear free energy relationship. So in this chapter, we're going to focus on just the gating part of that reaction scheme, namely hold and the other sub-events that take place between C and O. And furthermore, we're going to try to extend the view of catch and hold being linked as a zipper mechanism, which we described in chapter 3. We're going to try to extend that zipper all the way through the rest of the isomerization. This chapter is a little more complicated than the previous one, so I've divided it into 3 different sections. We're going to get at what's going inside the gating isomerization by using a parameter called phi, or phi, depending whether you use the Greek or the English pronunciation. I'll probably use both. So the first section of this chapter 4 is going to be the definition of phi, what its distribution is, and how we measure it. The second chapter is going to be the interpretation that we apply to phi. And that, I will warn you, not everyone will agree with that. That is something that we have developed, so you can call that a hypothesis of what phi really means. And then finally, we're going to combine the phi distribution interpretation with the linear free energy linkage between catch and hold, and zip up the acetylcholine receptor activation process. So let's start with the first section. So let's start by defining phi. You will recall, in both efficiency, given by this Greek letter eta, and phi are ratios of energies following a perturbation. So in the case of efficiency, the perturbation is the addition of an agonist. And the ratio that we're going to be concerned about is the stabilization of the C state provided by the agonist relative to that provided to the O state. So the ratio of these two blue lines, or 1 minus that ratio, is what phi is. And in words, phi, eta, that's what eta is. And in words, eta is the log correlation between efficacy and affinity on a scale from 0 to 1. Efficacy being the coupling constant, that's the log of which is the length of this area right here, and affinity, which is now we're talking about the strong affinity. And our interpretation we gave to that correlation is it's the fraction of binding energy that's converted into gating energy. Phi also is a ratio following a perturbation. In this case, the perturbation is usually a mutation. So we're looking at the gating equilibrium constants, the gating rate and equilibrium constants in the wild-type receptor and following a perturbation. And these energy landscapes are just examples. And what we're going to be taking the ratio of is the change in the transition state energy, the energy at the transition state, relative to the energy at the O state. So phi is the log correlation between an opening rate constant and a gating equilibrium constant, also on a scale from 0 to 1. In the case of eta, a value of 1 meant that the ligand was a perfect agonist, that is, all of its binding energy went into gating. And in the case at a value of 0, none of its value went into gating, so it was a perfect antagonist. In the case of phi, a value of 1 means that the change in the transition state energy following the perturbation was the same as that in the O state. So at the transition state, the perturbed region had a energy character that was open-like. And you'll see that that's not always true. Some of them are still closed-like, which would mean a phi of 0. So let's remind ourselves of the thermodynamic cycle, here shown in the form of energy landscapes, without and with agonists. And as you recall by this red line, that the stabilization of the transition state and that of the open state given by the agonists were approximately the same, which is why we have this mountain gets smaller and opening gets faster when agonists are present. So with our new definition of phi, that means that these two lines were approximately the same length, which gives a phi of 1 for the agonist at the transition state. Now, in order to emphasize the difference between phi and eta, the efficiency, has to do with the energies that we're comparing. In eta, we were comparing the energies of the ground states, A2C and A2O, but now we're comparing the energies of the transition state and A2O. So our focus is going to be really on the barrier region that separates C from O. So on the left side of this barrier is C, and the right side is O, and in between are fleeting intermediate states. This is a region of instability, and nothing lasts very long here. So we have structures of the C state, we have structures of the O state, but these states in here are occupied with a very low probability because they don't act very long, so it may be difficult to isolate these for gaining structures. But our focus is going to be really on this region right here. So as with the other chapters, I want to start here by showing an unexplained experimental result. everything in this video pamphlet was motivated by experiments rather than theory. And our discussion of what's going on inside the protein is no exception. So here is a histogram of 5 values for a mutational series of 137 different residues scattered throughout the protein, where we measure the change in the transition state and relative to that in the open state. And you can see there are 5 different populations. So in some regions of the protein, the bars were, as was with the agonist, that the transition state was open-like. In others, it was less so, 58%, 33%, and there is sort of a smear down here near 0, which came out to be an average of 6%. So the point here is that there are 5 discrete populations, and this was a surprise, partly because no one had ever measured this before, but also I think most people might have thought it's either going to be all 1 or all 0 or some division between the two, or perhaps scattered all over the place. But we see 5 different populations, and this is what we're going to try to explain in the second section of this chapter. But I just want to point out this is to measure each of these 5 values, of which there are 137. We had to measure maybe 5 or 10 different mutations at each site. So this is a huge amount of work that took about 18 years and 18 graduate students and postdocs to do. And I just want to show their names briefly here. If you go to the acknowledgement sections, I'll try to give them even more credit or explain their participation even more. But let's start with the agonist again. So here's a picture from 5-KXI, a neuronal nicotinic receptor, with the agonist here, nicotine, shown in pink. And an agonist is sort of like a side chain in the sense it's about the same size. But there are several important notable differences. First of all, it's not one of the natural amino acids, at least not in nicotinic receptors. It is in other receptors. Second of all, it's not covalently linked, which means it's free to come and go and serve as a signaling molecule. And the third notable difference is the wild-type agonist, which we'll call acetylcholine, a transmitter, is much more stable in the open conformation than it is in the closed conformation. Indeed, that's the definition of an agonist. It's a ligand that's more stable in the open conformation of the binding site compared to the closed conformation of the binding site. So this is in contrast to wild-type side chains, which in general are more stable in the closed conformation compared to the open conformation. So if you make a mutation anywhere in the protein, the odds are you're going to increase the unliganded gating equilibrium constant because you've substituted a side chain which is less stable in C than the wild-type side chain. Down below is our method of analyzing, estimating phi values, and that is from a REFR, a rate equilibrium free energy analysis. That's what this plot is. It's a plot of the log of the opening rate constant versus the log of the equilibrium constant. And the slope of that line gives you the ratio of those two blue lines, which gives you the phi value. So here is, each one of these symbols is a different agonist. They all fall closely on the same line, which has a slope of about 0.95. In some experiments, it's as low as 0.9. In other experiments, we've gotten the number 1. So on average, it's about 0.95. And these data are taken from this paper shown down below. So the agonist is 95% open-like at the transition state. And I want to show that water is on this plot. And water is the dividing line between agonists and antagonists. Anything to the right of this vertical line here is an agonist, and anything that would be left of this line would be an inverse agonist. And the line itself is what it is represents antagonist action. But we don't know of any inverse agonists of muscle nicotinic receptors. So the agonist is 95% like. What about the side chains at the binding site? Well, we have mutated all these side chains here and several others that are in the vicinity of the binding site. And in all cases, they fall into the high purple 95% class. So here's an example of a log opening rate, a REFR, for mutations of this residue here, W149. So each symbol here represents a different side chain substitution. And there's no agonist in this case. This is just spontaneous unliganded gating. So all the information is from the intrinsic isomerization. And we can see we get a slope of 0.88, which means it's 88% open-like at the transition state, this side chain. Now, when you add an agonist, it goes up to 0.97. So the agonist is contributing a little bit, maybe a little bit higher than the intrinsic isomerization. But the main point here is they're both in the purple high phi population in that distribution. So everything at the binding site that we've measured so far is in the purple class, purple population. We're going to call that hold, and we're going to associate that with the switch of the binding site from low to high affinity. So in A2C, the ligand is bound with low affinity, and after hold, the ligand now is in high affinity, and it remains that way all the way through the rest of the gating process. This slide shows reefers, rate equilibrium free energy relationships, for about 25 or so different side chains. So each panel is a mutational series of one amino acid somewhere in the protein. So for example, this reefer is for L228, which is in the M1 helix, and each point is a different mutation with a different side chain, with the 0,0 point being the wild type. So in this case, all of the mutations reduced the gating equilibrium constant, made it smaller. But we fit these reefers to a straight line to get a phi value for that residue. In this case, it was 0.67. And we do this over and over and over again, not only for those 137 residues shown in the histogram, but probably for another 100 or so, in which case we made mutations, but the spread along the equilibrium constant axis was too small to get an accurate slope measurement. So we only are plotting in that histogram the 137 residues where mutations made a significant change to the equilibrium constants. So each one of these is a plot of log opening rate constant versus log equilibrium constant, actually relative to that of the wild type. 0,0 is the wild type. Now, we used agonists to activate the receptor in all these, so this log L2 is really the sum of the log L0, which is the intrinsic gating equilibrium constant, plus 2 times the log of the coupling constant. So we really are measuring the sum of these two things when we measure this with acetylcholine, for example, or choline, depending on what agonist we use. And the point I want to make here is that we think that we're only changing log L0 when we make mutations away from the binding site. So each of these reefers represents the phi value of the residue in unliganded gating, and it's not being influenced by that coupling constant. Experimental support for that assertion that mutations away from the binding sites change L0 but not the coupling constant is shown in this plot here. This is a plot of the effect of the mutation relative to some background on unliganded gating versus its effect on liganded gating with some agonist presence. So agonists were present on the x-axis, agonists were not present on the y-axis. And each point is a different mutation or combination of mutations. And this is for both the adult type receptor in solid circles and the fetal type receptor, which has a gamma subunit between the two alphas, shown as open circles. And the main point here is that the slopes of both of these lines is 1. That is, whatever you did to change the diliganded gating, you also did change the unliganded gating. The effects on unliganded and diliganded gating were equal, which means they did not affect the coupling constant. That effect was the same for both. And in fact, we use this when we extrapolate these lines to the point where there was no effect of a mutation on diliganded gating, we can read out what the unliganded gating rate constant would be, and this is the way we use one of the ways we use to estimate the unliganded gating equilibrium constant of wild-type receptors. But that's another story. That's going to be presented, I think, in another video on unliganded gating. But the point here is that it is true that mutations away from the binding sites do not change the coupling constant. So what we are measuring in our Phi plots is the unliganded gating Phi values of different residues. So here now is the histogram showing you once again what it was like with diliganded gating. And what we found is that both that 149 and there's another one, 198, change significantly with and without agonists. So we can make a new histogram which just shows the unliganded gating, and we still have our 5 populations, and we see a slight difference in the numbers of what the values are. But basically we're looking at when we looked at this histogram, we're looking at the unliganded gating. But I'm going to stick with the diligated histogram for the rest of this talk. So the rest of this chapter is going to be concerned with the interpretation of this histogram. We now know what Phi is. We've defined it. We now know how it's measured, and we're now looking at the distribution of Phi for diliganded gating, and that brings us to the end of the first section. And in the following section, we're going to try to understand what it is that Phi is telling us, this distribution is telling us.